And welcome to another video of CS360, and this time we will cover Kolmogorov complexity. Kolmogorov complexity. So Kolmogorov complexity is this notion of basically trying to do compression, really well of strings. So consider a given string. So what is kind of the best way to compress it? And okay, so you can say maybe there's no best way, but in some sense there's sort of a best way to compress a string, right? Because if you can compress a string, then you can decompress it, and if the decompression is via some computation, then you will have some program that decompresses the string. So some program that takes the compressed version and decompresses it. And then we can imagine kind of hard coding this decompressed version into the program. So let's say we have W and we will compress it to a string CW, the compressed version. And then like suppose we have a decompressor machine that takes M of CW and gives us W, right? So it takes in this compressed strings and gives W. So now imagine that I hard code the CW into M, and then I'll get a machine basically hard coding it just by making the string part. I'll make a new machine, basically MCW, that on input epsilon first write down CW on the tape and then runs M. So this is it outputs W when run on the empty string. Okay, then in a sense, this machine MCW, a description of this machine is a description of a machine that when run on the empty string generates W, right? So I have here a machine that when run on the empty string generates W. Okay, and if the number of states of M is some K, then the number of the description length here of this new machine MCW is going to be something on the order of, so roughly K plus the size of CW. That's going to be this description length of this machine. So, if we think of the string as being really long, or as this part as being long, and the decompression program as being some fixed size program, so if we think of K as a constant, then essentially, just by giving you this one program, I basically gave you something that's almost as small as the compressed version of the string W. And yet you can decompress W just by running the machine. Okay, so I guess what this is saying is that giving you this is sort of as good as giving you any compressed version of W. So it's sort of better than any compression protocol in this sense, up to these this factor of additive factor of K. So up to this overhead. If I want to compress W to a string CW, such that it's possible to decompress it via computation, then I might as well just give you this type of string, and you would decompress it just by running the machine. So I might as well just give you this compressed version. It's not going to be too much larger. It might be somewhat larger. And you can still decompress it just by running the machine on the empty string. So this is called Kolmogorov complexity. So Kolmogorov complexity of a string. So the Kolmogorov complexity of a string W is the minimum description of a machine such that this machine outputs W. Okay, so in particular it has to hold one run on the empty string. Okay, so it's the minimum, the minimum description length of a machine, which outputs W. Okay, So this is called K of W. So it's denoted. Okay, so it's sort of like the how much I can compress W using this Kolmogorov compression, where I give you a description of the machine and you run the machine and that will generate the string W. And this is sort of better than any other compression protocol in terms of the size of the compressed string, except for some overhead. Okay. So that's nice. Note that K of W is not much bigger than W. So it's not going to be too much bigger than W. It's going to be at most like O of the length of W, where I'm using kind of big O notation to hide constant factors. And that's because I can always give you just the machine MW that basically has W hard coded in. So this machine has W hard coded in. So if you so it uses this many states to write the characters of W one by one. Okay, and so if I have a machine with this many states that just write the characters one by one, how long does it take for me? Sorry, how much memory does it take for me to describe this machine to you? And you know, it turns out it's only some constant amount per state. I just need to tell you, like, to describe this machine. So it's you know, it depends a bit on my notation for how I denote machines, but it should be linear in this number of states and the size of W. So this Kolmogorov complexity basically doesn't really get larger than the length of the string W, but it can be smaller. So for example, if I think of the string 0 to the n, where n is something really large, and it's a large number, natural number. So this is a string of all zeros. Then I can generate the string basically by a program that has n hard coded in binary. Okay, so you know I can have a machine with only log n with log n states to store n, and you know this machine. Oops. So it will write n in binary on the tape, then print that many zeros, and then erase the original n that's written on the tape. So this machine will only take log n states plus some constantly many more. So maybe it will be in the end log n plus 10 states or something. But with only this many states, I can generate to this string 0 to the n in the end. Okay. And so that means that k of 0 to the n will be something on the order of log n. Okay, I'm using this big O notation to hide constant factors. But so k on the Kolmogorov complexity of the string is going to be much smaller than n, even though the string is of length n. So this is a string of length n. The length is n, but the Kolmogorov complexity is much larger. You can compress it into a much smaller program. Okay, and generally any string that has a pattern. So for example, a string that looks like this. You can imagine a program like you can even use your favorite programming language. Think of a program like a Python program that goes, you know, for or whatever for I, you know, just your favorite programming language. You know, print 0, 1, something like that. So you know, you've printed this whole string, but you only needed to store. What did you need to store here? You know, you only needed to store the length of k. So k here had to be hard coded in because we want to print this one specific string. So k had to be hard coded in, but this takes log k bits to store k. And then to store the rest of this description, this is like 2 lines of code. So this takes not very many bits to store this, just some constant number. Okay, so the Kolmogorov complexity of this string is on the order of log k. Okay, and so generally, if you can write a program to generate the string, which is much shorter than the length of the string, then the Kolmogorov complexity is low. Okay, and so this is sort of like the best possible compression in the sense of how small the string is that you get is, and in the sense that the strings you get in the end, the compressed string, can be decompressed computably. However, the compression itself is uncomputable. So the next thing we will show is that this function is uncomputable. It's not computable. There's no machine that can compute it. So that's too bad, right? So, and then the proof of this is kind of like the paradox. You know, there's a paradox that goes, consider the smallest number that cannot be described in less than 1,000 English words. So of course, there's only finitely many numbers that can be described by 1,000 English words or less, because there's finitely many sequences of 1,000 English words. So that's only finitely many numbers that can be described by 1,000 English words. So consider the smallest number that cannot be described by 1,000 English words. This exists, the smallest natural number. Okay, so I just described it. So this is the paradox. If I just described it, but I used less than 1,000 words. I mean, I talked for a while, but it was less than 1,000. So how can that be that I described the smallest number that by definition cannot be described in less than 1,000 words, yet I described it in fewer than 1,000 words? So this is kind of this paradox that you may have heard of before. And we're kind of trying to do a more precise version of the paradox. So the problem with this paradox is that it's not clear what we mean by being described by English words. What should that mean formally? So we're going to do that with Turing machines now. So we're going to say something like, consider smallest, string in or first string in lexicographic order, for example, that cannot be described by a TM of less than n states, or less than n states, or less than n description length. So the number of states and the description length of the machine are sort of similar concepts. Okay, so consider the smallest string w. So this is sort of the same as the start of this paradox. Consider the smallest number that cannot be described. So this is the shortest string w, I guess. Okay, so, or the first string w in lexicographic order. So now we want the punchline. I just described it, right? But then, okay, so how do we kind of describe it? So suppose the Kolmogorov complexity was computable. So actually, let's just change this slightly. So instead of by a TM of less than at most n states, by a TM let's write by a TM m with the description length of m being less than n. Okay, so okay, so we consider the smallest w that cannot be described by it. Okay, so of course there's only finitely many descriptions of length less than n. There's only finitely many descriptions, and therefore only finitely many Turing machines with descriptions of at most this long. So only they can only describe finitely many strings, right? And by describe, I mean we want m of epsilon to equal w. So that can only happen for finitely many strings that they have description length less than n. That basically they have Kolmogorov complexity less than n. So this is basically saying equivalently, this is like consider smallest string. That's right. smallest string W with K of W less than N. So this is equivalent, okay? And now we want to say the punchline. I just described it in less than, description length N Turing machine. So how do we do that? So, well, we would assume that, to do that, let's do the following. So first of all, assume that the Kolmogorov complexity is computable. So say that K is computed by TMT. Okay, so then we describe a TM P. Okay, and then P, it does the following steps. It says go through all strings in lexicographic order, and then run T, let's just all strings X, run T of X to get K of X. Okay, so this is like step 2. And then if sorry, I think I messed up here. Consider the smallest string W with K and not less than N. Sorry, with K of W greater than N. Yeah. So this is the string we want to consider there. Sorry about that. Okay, so we go through all strings X in lexicographic order. We run T of X to get K, and then if K of X is less than N, output X and halt. Okay, so this is the program P, and this is what P of epsilon does. Okay, so let's call it P sub N because there was a dependence on number N here. Okay, so let's just try this again. P sub N of epsilon. Okay, so iterate over, over strings X in lex order, in lexicographic order. Compute K of X, assuming this is computable. Output X and halt if K of X is bigger than N. Okay. So we are looking for strings that have Kolmogorov complexity more than N. Okay. And then, so how long does this take to do? So this first step of just iterating over strings in lexicographic order, can be done in constantly many states. This is just a fixed line of Python code, basically just a for loop. This compute K of X, the number of states you need for that is the number of states in T, right? We had some fixed T that does this. So for this part, we just need to call a subroutine for T. So this is a fixed number of states, it's a constant number of states. And for this part, we only need a constant number of states plus the description of N. So we need log N states to store N. Okay, so Pn here uses something like log N plus O1 states. And by that, I mean that this is some constant that's not dependent on N. Okay. So for large N, for some large enough N, N is basically bigger than this description length of Pn, because the description length of a Turing machine is proportional to the number of states. So for some large N, the N itself is bigger than the description length of Pn, because the description length of Pn is going to be on the order of log N plus some overhead that depends on how many states you need to complete the Kolmogorov complexity. So for when that happens, then what we have here is we have a machine Pn that on input epsilon will output some string x, uh, you know, uh, you know, with k of x bigger than n. So yet the description length is smaller than n. So what we have here is, by definition, the Kolmogorov complexity was the description length of the shortest program that output x. But here we have a short program, Pn itself is a short program that outputs x. It's short because its description length is less than n. And yet it sort of, by the guarantee of Pn, it output a string where the Kolmogorov complexity was more than n. So this is a contradiction. It can't be both less than n and more than n, basically. And this contradiction basically is basically this formalization of the paradox. What we did here is this Pn is formalizing the part where we go, we just described this number in less than 1,000 English words. So this is sort of what we're trying to say here. We're trying to say we just described the string x, the first string that does not have Kolmogorov complexity less than n. The first string that cannot be described with a Turing machine of less than n description. So this is the first string x. We just described it with a Turing machine of less than n description. So this is Pn. Pn is the part where the punchline comes from for this paradox. And that works. The Pn only has description length on the order of log n. So that works so long as the Kolmogorov complexity was computable in the first place. So long as this was computable, then this paradox would work. Okay, so the paradox working actually gives us a contradiction. So from this, we actually conclude that the Kolmogorov complexity is not computable. Because it's not computable, this paradox actually does not go through. So we fail to describe the string x in this Turing machine version of description. We failed to create a Turing machine for finding the string x. And the reason we failed to find this x with a Turing machine is because we cannot compute Kolmogorov complexities of strings. Okay. So the conclusion is, even though the Kolmogorov complexity sounded like a great compression scheme, it's great for decompressing, I guess. I mean, the decompression is computable. And the length is pretty good, for the best out of all compression schemes up to constant factors, so long as they have computable decompressions. But the compression part, like figuring out how to compress a string, how to turn it from x to a machine M that outputs x and has minimum length, and where this is small. So this conversion here, this arrow, is very hard to compute. In fact, it's uncomputable. So you cannot go from a string to the smallest machine that outputs that string when given empty input. Okay. So unfortunately, it's not a very useful compression technique, because we can't compute the compressions itself. We can only compute the decompression. Okay, so this was the notion of Kolmogorov complexity. So it's a pretty cool notion. I think it kind of, you can view it as almost a philosophical concept of what is the shortest description length of a string, or you can even think of it as an image. How short of a program can I come up with for generating a given image? How short of a program can I come up with for generating all of Wikipedia? All the Wikipedia articles. Maybe it's not that long. Maybe you can, imagine that Wikipedia articles, all you need to know is, some knowledge about the real world, and if you kind of had that knowledge in some kind of very succinct, compressed, brain-like form, then you would only need to remember a few stylistic details, and you would have a compression of Wikipedia that's of short description. Anyway, so unfortunately, we cannot compute these things, so we cannot actually answer this question of how short of a program can generate Wikipedia. Okay, so I'll see you next time.